Okay, let's quickly run through Euler's method. Very, very easy process. There's one formula you need to know here. This is yn minus 1 plus h f x n sub 1 minus 1 y n minus 1. This is the formula you can see above. And what this means is it looks very complicated. However, if I had to break this down in very simple detail, this is your initial y, so your first y that is given. H is something that's known as the step size, and this is also usually given. However, if it's not given to you, all you do is you look at, let's say for example this is 1, 2, 3, 4. What is the change in x? Well, the change in x we can obviously see is 1, right? So if the change in x is 1, that means your step size is 1. Okay, so if it's not given to you but like 4 coordinates or 3 coordinates is given, then you can quickly figure out h by just looking what's the difference to it. And this thing over here, although it looks complicated, this is literally just the differential where you substitute your x and your y. So that's all you do, you substitute your x and your y. Now as I'm explaining, I realized that use Euler's method with a step size of 0.1 to construct a table. I can't solve this one because there's no differential, which means I'm going to start by the second one. My deepest apologies. Anyway, let's see. So we discussed a simple electric circuit with a resistance of 12 ohm, inductance of 4H, and a battery with 60 volt. If the switch is closed T0, we can model the current at the T time with the initial value problem. Okay, so we're given our initial equation, and notice they give us our differential. So our differential is di over dt, 15 minus 3i, I being the current. Okay, physics students should know that. Then we can see, well, I, when time is 0, the current is 0. Okay, so what do we have here? Well, we have our initial condition. This is our initial condition. So there's 2 things you need to spot here, or 3 things you need to spot. It's our initial condition, you need to spot your differential, and then you need to spot your step size. However, in this case, the step size is not given, but we can logically deduce here what a step size could be for this particular example. Okay, so estimate the current half a second after the switch is closed. So they want 0.5 because half a second is obviously 0.5. So to get the most approximate or most accurate approximate, I'm going to use a step size of 0.1. So this is how our setup is going to look. Watch this. Okay. Firstly, we need to figure out what our x's are going to be. But the x's are very, very simple. So for this case, we can say, well, time is equal to 0. So just take your step size and plus it by the x. So it's going to be 0.1, t equals 0.2, t equals 0.3, t equals 0.4, and then t is equal to 0.5. That's it. That's literally it. Very, very simple. Now, we plug this into our formula. What is our formula? Our formula is yn is equal to yn minus 1 plus h f and our differential. Okay, so what are we trying to find? Well, we're trying to find current because remember, in this particular case, it's not easy anymore. So in this case, our y is our I and our x is our t. So I need to find the first current. So look how I do it. You plug in 0 plus the step size, 0.1, and then you plug in your differential and you plug also y again. So it's going to be minus 3 and then 0. Okay, then we can find our first I. So let's check it out. Okay, I need Desmos. Let me open up Desmos, hold on. Scientific calculator. Okay, what do we need? So we need 0.1, 15 minus, that's it, 1.5. Okay, so our first I is 1.5. Now for I sub 2, I'm just going to plug in. Here's the tricky part, okay? You got your new x, so t was 0.1, so that's your first x. Now your new x is 0.2, but in this case it's t. But for this particular differential, we don't need to use the t because we only have I. So look what I'm going to do now. I'm going to take my new I and then plug it into the next point. And that's it. That's literally the process. Now you just repeat however many times you need it. Well, we need when t is 0.5, right? So I need to do this 5 times. So I need to find I5. Okay, so let's plug in this differential. 0.1, 15 minus 3, 1.5. So we get 2.55. So 2.55. Now we use I sub 3. And would you have guessed it? Oh, just plug in the new points. Easy peasy. And you'll see when you solve the differential, it's actually pretty close to your original or the approximation. It's pretty close. Okay, so let me just 2.325. Okay, so that was what? 3.285, right? 285. You can't make a mistake here, by the way. You need to... Okay, so what do we do for I sub 4? Oh, can you believe it? We're going to plug in the same numbers. Plus. Notice that the step size never changed, right? The differential also never changed. It's just the new values that gets plugged into the equation. And that's Euler's method of approximation. Okay, so let's plug it in. I'll make a video later on how to solve it on the graphic display calculator. So it's 3.995, 3.7995. Okay, so now we can do it one more time. I5, Intel Core i5, 995 plus 0.1, 15 minus 3, 3.7, sorry, 995. That gives me what? Okay, 4.16. I'll take 4.16. So 4.16. Okay. So now how do we write this? Well, we can now say, well, where I for 0.5, which is time, is going to be approximately equal to 1.46 amperes. And if we had to actually solve the differential and then plug in our initial condition, or plug in 0.5 because that's what they want, we'll get very close to this answer. And this is pretty much how you do Euler's method. Okay, so you find your new points, plug it in, boom, easy. Okay, now I want to look at this example. So this would be an IB exam example. It was one of the examples given, so let's check it out. So they gave us, we can clearly see. So first, let's write down what we know. We know that the differential given is EX plus 2y squared. You see, if you had to try solve this differential, it would be pretty complicated. Look at our initial condition. This is also given to you. Our initial condition is where y of 0 is equal to 1. So that's our initial condition. And then all we need to do by ourselves is figure out the step size in this case. In this case, we can clearly see the step size is 0.4. So I'm not sure what this question was, but I could assume that the question was, use Euler's methods of approximation to approximate with the step size of 0.1 to where x is 0.4. I would assume that's the case. Anyway, let's set it up so I can show you how they got their answer. So I'll just write the formula again, as I always do. Yn plus h. In the IB booklet, it's a little bit different, I think, if I remember correctly. Anyway, so what do we need to find? We need to find y sub 1. So let's go find y sub 1. We plug in our initial condition. So our initial y is 1 plus our step size was 0.1. we plug in our differential with our substituted values. So check e to the 0 plus 2 1 squared. Okay, let's plug this in. How's it gonna work? Okay, what was it? 1 plus okay, so look at that. We get 1.3. Look at IB's answer, 1.3. You see that? Boom. 1.3. Now, here's the tricky part. So now we know you can construct a table like this, by the way. The table they constructed is very nice. That's usually how I would teach how to construct a table. So 0, 1. Now we know with our step size added, it's 0.1 and we got 1.3. Now here's the tricky part. You're going to have to take, look, 0.2 because we added the step size. So look now, to find y sub 2, all you do is you plug in your new y. Because this n minus 1 essentially means y2 minus 1, which is y sub 1. So now you take the y sub 1 you just solved and you plugged it into the next differential. Step size stays the same as always, e raised to the 0.1 in this case, plus 2, and then our y was 0.3, 2. Okay, let's see what we get. Plug it in. Remember, the reason I'm using, you might be confused, is it's like, oh, so why aren't you using 0.2? Because we're calculating for 0.2 here. Well, remember, to find the second point, I already know what my step size is. And then in that case, we know we also need to use xn minus 1. So look, in our initial formula, xn minus 1. So that's 2 minus 1, right? Which is 1. So in that case, we use 0.1. Okay, let's check it out. So now I need to change this with 1.3 and then 1.3. And this one was 0.1. Quite a big number. Anyway, I'll just confirm by looking at the box. Okay, so check. You see, 0.2 gives us 1.7, the exact same thing I found. Now you take this 1.7, this long number, you plug it in, use 0.2, and you find the next information. You see? You find the next information. And then let's do it one more time to find the final answer. What's that? It was 0.3. So that's going to be 0.3. And then, oh, whoa, I need to copy all of this. Yeah, it's a bit of a lengthy process for sure. Requires you to spend time on the calc. Anyway, so see, 3.5, and we get our final answer, our very final step size. Okay, so now this dy dx you can then also solve on the calculator, because you can plug this differential on the calculator. So what I'm going to do is, I don't have my graphic display calculator next to me. However, I'm going to use, hold on. Okay. You plug in that differential. It was e raised to the x plus a y. What was it? 2y squared. Okay, so let's see what the differential is. What's the differential? Huh? Damn, they don't even give us the differential. Hell no. But anyway, that would sort of be what you're trying to do. I'm not too sure what the full question is in this particular case. dy dx, I'm assuming you just plug in these values, right? You just plug it in. Let's see. I'm sure that's what was asked. So it would be e raised to the 0 plus 2 1, that was 1. Okay, so there you just plug in the original equation. So for the next one, what would we plug? Oh, we plug into the differential. It would then be 0.1 and 1.3. Hell nah, we don't get it. Oh, sorry, it's a square. Excuse me. Raffle. Okay, square. So we get the next one, and I can just continue doing this. That's how you would solve this IB equation, by the looks of it. So that would just be the next one. You just plug in, and you keep plugging in, right? So you just plug in the Euler's values into the dy dx. Okay, very easy. And then for this one, you can just solve that one on your GDC. But yeah, anyway, that's how we do it. Okay, everyone. Oh my goodness. Have a lovely day.